John.
Thank you so much, Salar, and thank you for the invitation to speak here. So tonight, me and Adam are going to be talking about refactoring functional type classes. We're unveiling the design for a new library called Zeo Prelude that's designed to give you a totally different take on what abstractions can look like in the context of functional programming. So I asked Adam to join me for this talk because he's worked on this library extensively with me. In fact, right now he is the #1 contributor. His own contributions outstrip my own. And he's gotten there by polishing, by adding a ton of cool new data types and features and instances and tests. And so I asked him to co-present with me tonight. Adam, you want to say a few words?
Yeah, absolutely. Thank you so much for the opportunity to work with you on this. It's been great, as well as working with you on all sorts of other fun things Zeo related. Thank you for everyone here who's joining us, especially people who I know it's late for those who are listening in from Europe. And thank you for everyone who's either contributed to the library or given feedback or ideas during the process. We're really excited to share what we've been working on with you.
Yeah. You ever get that feeling of deja vu, like you've been in this situation before, maybe saying these same things before? That's happening to me right now. Anyway, let me tell you why I'm here giving this talk. It's because about 8 years or so ago, I actually set out to create a successor to a library called Blue Eyes that I created. And this library, it was designed to give you a client and a server in a type-safe fashion from a single definition of a route, an HTTP web route. And I remember banging my head against the wall because as I was developing the data types that were going to make this possible, I thought I saw something from the traditional classic functor hierarchy. I thought I saw an applicative and a monad and other things like them, but I couldn't create instances of these type classes for these data types because it wasn't quite right. It was like they had some of the structure, but it wasn't formulated in exactly the same way. And so fast forward to many years and experiments and my work on Scalaz and 8 and more study of category theory and all this stuff, I've come to the conclusion that there's something not quite right about the classic functional programming hierarchy. And there's always going to be something wrong with it, right? Because these programming languages that we use, they have restrictive type systems and we're not able to express math the way math is expressed in books and in papers. But potentially we could do better. Potentially there's a different factoring that would open up a whole new world of design choices to us today. And I think we've found that in Zeo Prelude. Tonight I invite you to follow along for the tour. I hope that if you are new to the functor hierarchy, then you're left today with a profound sense for how all these different abstractions are connected in a very simple way. A simple way that you can probably fit inside your head, even though if you've never seen Functor before, you'll probably be a little confused tonight. But I hope when you come out, you'll have a sense for what this structure is and you'll feel like it's reachable. It's something you could reach in a few hours of study or a day or two of study. I think that's actually true. And on the other hand, if you're a new, or if you've been functional programming for weeks or months, so you already know Functor, you use Monad on a regular basis, then I hope that this opens your eyes. I really do, because the type classes that you use, they act as a filter on how you see the world. You can't see structure that doesn't exist, that can't be encoded in these type classes until you get a peek sort of at what the real world is like. And what I'm going to do tonight is hopefully give you that peek. So you'll be able to see new structure in the type classes you use, but also know when those type classes are holding you back, when you need to take a step back and introduce data types that maybe can't be described by those same type classes, but maybe could be described by something like Zeo Prelude. So tonight we're going to talk a bit about the functor hierarchy, and if you haven't seen it before, you will see a very brief tour of it. Adam's going to do that introduction and talk a bit about the significance of the functor hierarchy in commercial functional programming. And then I'm going to take a detour and talk about some of the drawbacks of the classic functor hierarchy, not just the way it's structured, but also the way it's applied in Scala. And then we'll switch over to Adam, and he'll talk about algebra, easy algebra, so not the kind you may have run from before in high school or college math, but very simple algebra that could potentially form a basis for a new type of a way of thinking about functional programming abstractions. And then finally, in the final segment of the talk, both Adam and I will be introducing Zeo Prelude, which is an algebraic, modular, and Scala first take on what it means to do abstraction in functional Scala. Adam?
Great. So before we can talk about alternatives to the functor hierarchy, we need to understand a little bit what the functor hierarchy is and why it's been so influential. So to start with, functor is what we call a type class in functional programming. So it describes some similar functionality that exists across different data types. And so at the top of the hierarchy here, we have this thing called functor, and then below that we have applicative. Sorry, I'm going to try to speak a little bit more loudly. So we have functor, applicative, and then monad. So functor sits at the top of that hierarchy, and functor describes some type that is a type constructor. So it's parameterized other types. So think about an option or a list or a future in the Scala standard library. And this describes some type of value in a context. So if you think about having a string, if we just have a string, we just have a name, we just have Adam. If we have a option of a string, then we may have a string, or we may not actually have a string at all. If we have a future of a string, then we may at some point in the future have a string, we may not have a string at all right now. If we have a list, we may have no strings, we may have one string, or we may have 100 strings. And so functor describes a common functionality we have across all these types of being able to do this map operation, which essentially says that we're able to transform the value inside that type while keeping it within that type. So mapping over an option means I don't know if a value exists or not, but if it does, transform it with this function. Mapping over a list means I don't know how many values there are in this list, if there are any, but whatever values there are in the list, transform them with this function. On a future, it means I may not have a value right now, but whenever I get a value, if I do, transform the result with this function. The next step down the functor hierarchy is this thing called apply. And this adds this method app, which has a little bit of a weird signature that we'll talk about later, but essentially lets you put two of these values in a context together. So you can imagine if I have a future that's going to return someone's first name, another future that's going to return their last name, I can take those two together and return a new single future that has the first name and the last name. The next thing in the hierarchy is applicative, which is the first thing that gives us the ability to put a value into this context in addition to just working with values in the context. So you can imagine if we have a future, I can now put an existing value into a future. If I have an option, I can put a value into an option. And this ends up being important because this gives us the ability to describe parallel computations. So you'll often see applicative used when you want to do some degree of parallelism or you want to do multiple things at the same time. And then the final part of this hierarchy is this monad, which adds this flat map operation. And whereas that app operation we talked about before lets you take two different values in a context and just combine them together, this flat map operation now lets you take one value in a context and use that value to generate a new value in a context. So if we think about like having a future, that app operation would be like zipping futures where you say, I've got these two different database queries and take the results of both of them and combine them together. Whereas flat map is saying, I'm going to do one database query, and then once that comes back, I'm going to use the result of that to create a whole new database query. And so this essentially lets us embed a model of imperative programming into functional programming and gives us all the capabilities that we can do literally anything we can do in an imperative programming language in a purely functional context just by embedding it into these flat map computations. And so this has really been incredibly influential, starting off in Haskell and the way they encoded the IO monad there, but then going over to Scala in the Scalaz library, as well as Cats. Really, a lot of what they've done has been based on this, as well as you've seen this go into a lot of other programming languages of like Kotlin, Java, F#, as well as a ton of different Scala talks you've probably seen about what a monad is. And we've learned it's a monoid in the category of endofunctors, or maybe it's a burrito. I don't really know. But it's, in addition to just being influential this way, it's powered a lot of real solutions. So you can think about libraries like HTTP4S or Doobie. Monads have really been the tool that libraries in Scala that have tried to use functional programming to solve real business problems have used, and also inspired a ton of books, from the Red Book, Functional Programming in Scala, that probably a lot of us have read and got used to get started in Scala with functional programming, to newer books in Scala, to books about F#, books about doing functional programming in Python, in Java. So it's really been incredibly influential, and it's let us really get to where we are today. But as we're going to see, there are also some problems with it.
Yeah, that's right. So while the Functor hierarchy has proven itself, I'd say, in commercial functional programming, and does deliver value and allows us to abstract over data types that all possess similar degrees of structure, it's not without its problems. And what I mean by this is that even in its original Haskell form, by the way, which was very messy originally and got cleaned up actually a little bit over time, it has some issues. And not just in its natural habitat, Haskell, but also when it's translated into other programming languages like Scala. Sometimes some things don't work well in Scala. They don't fit quite right. I call those things Haskellisms. So in this section, we're going to take a look at those things that both don't make sense in the original hierarchy maybe, or could be done in a little bit better fashion, and also those things that are merely drawbacks because of the way that we ported that over into Scala. So at the top of my list is the one I love to hate on, and that is the app method in the applicative type class. So this is a really weird operation. If you squint, you can see here that app is basically combining two Fs together. So that's what it does. It's a binary operator. It takes two Fs, so two futures or two options or two lists or something, and combines them into one. That's the simple part. That's the easy to teach part. The hard to teach part is over on the left-hand side, you have this function a to b that's stuck inside one F. And on the other hand, you have a value, and this binary operator is combining them in such a fashion that the function is applied with that value to yield the return value of the function. And so the first thing people ask is, why would you ever take a function and stick it inside a functor? Why would you ever stick a function inside a list, or a function inside an option, or a function inside something else? And honestly, there's only one good reason for that, and that is if your functions are always curried. So the reason why app has the signature, the very weird signature it does, is because in Haskell, 100% of all functions are curried. That means there are no multi-parameter functions in Haskell. If you have a function that takes 3 parameters, then it's actually a function that takes a value, that returns a function, that takes a value, that returns a function, that takes a value, and returns the value. And if you have curried functions everywhere, then it turns out if you're programming with a data type that possesses the structure of an applicative functor, then one of the most common things you want to do is take a pure function and apply it to n values, where these n values are all computed using this functor context. And to do that, you can use this app operator. Actually, the app operator has a symbolic alias, which is angle bracket, and then the star inside it. And what you do is you just lift that f function up into the functor context by using another weird operator. And then you just apply one argument after the other, separating them by the app operator. And that works out beautifully in Haskell. It allows you to actually, very painlessly, I think, use these applicative functors with ordinary functions with a minimum of fuss and a minimum of pain. And there's potentially better ways to do that, like applicative do and idiom brackets. But nonetheless, this app operator, it's fairly easy to use. And that's the reason why it has the structure it does, because all functions are curried in Haskell. In Scala, functions are not curried. In general, we don't curry our functions. We have n-ary functions in Scala, and actually we have functions from tuples to other tuples. Those are two different things, but never would we ever want to use this operator. In fact, the operator we would want to use is often called zip, because it would take an f of an a and an f of a b and zip them together to give you f of a tuple of a and b. That's a useful operator. That operator I can teach in 30 minutes. This operator here that we import from Haskell, it takes me 2 hours to teach this in the same fashion, because I have to teach about where it comes from and why this function here is sitting over in a functor context. Another example of the functor hierarchy going wrong is if you've tried to use set as a functor inside Scala or Haskell, then you've run into trouble. And the trouble that you run into is that no one ever defines an instance of functor for set. There's a good reason for that. If you try to define an instance of functor for set, then you run into a law violation. And the law violation, it's a violation of a law called the functor composition law. The functor composition law says that, let's say you have two functions, f and g. F goes from a to b, and g goes from b to c. Then the functor composition law says that you can map over this set first by f, so turn all the a's into b's, and then map over it by g, so turn all the b's into c's, and that should be equivalent to taking that set and mapping it over the composition of f and g. So composing those two functions into one function that goes all the way from a to c. Now, it's easy to come up with law violations of this for set, and the reason is that set in Scala is implemented using equals and hash code on the data type itself. It's a hash set. And so it uses equality and hash code defined on any object in Scala. Scala is an object-oriented programming language, and everything extends any. And any has two methods on it, or actually several methods, but two of those methods are equals and hash code. And so the Scala hash set implementation uses those. Well, there's a problem, because let's say we have a data type A for which we have a sensible definition of equality and hash code, and a data type C for which we also have a sensible definition of equality and hash code. Then when we compose those functions together, we go all the way from A to C. Okay, so that means we can map over the set using the compose function, and we get back something sensible. But what happens if we first try to map from A to B, and that gives us another set? Well, the contents of that set will be poorly defined, because if equality and hash code is not defined on the B's, then that means we might end up with some collisions. The set might delete information, or it might not delete information that it should be deleting, either of which would alter the structure of the set in such a way that we could actually observe it when we compose these functions together and do it the other way. So for this reason, set is not a functor in Scala and in Haskell and in other programming languages that have adopted the functor hierarchy. Well, this comes as quite a bit of a surprise to mathematicians, because in math, set actually does form a functor. So what's up? Well, the problem is that the thing that we call a functor inside of functional programming is actually a super specialized type of functor in mathematics. Basically, it's like we've looked at a whole universe of possible functors, and we've narrowed our scope onto a little tiny dot inside that universe and said, this is the thing that is a functor. Well, that's wrong, actually. That's not a functor. That's a very specific type of functor. It's an endofunctor in a very specific category in Scala. And that thing, just because something doesn't fit into that pattern doesn't mean it's not a functor. Because math is gigantic, and the set of all possible functors out there is enormous. And the amount of structure that you can describe with that concept in category theory, it's huge. You can't describe set as a functor using our type classes, but that doesn't mean it's not a functor. And this problem is pervasive across the entire functor hierarchy. Basically, it's a lie. You know, if you want if you want to do the precise thing and give things precise terminology, you have to come to the conclusion that we should not be using these terms like functor and so forth in FP libraries, because we're not being precise. We actually are referring to very super specialized versions of these much more general purpose abstractions. And you can see that this same problem arising not just for set, but in lots of other cases. An example is there's a library called Zeo Config. And it allows you to build up a description of configuration information, the structure of your config. And using this definition of what your config looks like, it can generate readers that can read configuration information from command line or environment variables or HOCON files or JSON or XML, YAML, DAW, whatever you can imagine. You can read information in from that format. You can also write to any format. And you can also use that definition to produce documentation, markdown documentation or HTML documentation with hyperlinks and examples. You can use it to produce reports that tell you where information came from. And you can use it to do all these really amazing things. And if you look at this data type and the operations on it, you're going to find operations that are very alarmingly similar to the ones that you would find on Functor and Applicative. But there's no way to create an instance of these type classes for this data type in Zeo Config. And that's not because Zeo Config's data type does not form a very valid abstraction with the same level of structure, just tweaked in a slightly different way. It's because the type classes that we're using are unable to conceive of these things as being instances because the structure is just not quite right. In a similar way, there's a library in development called Zeo Codec that's designed to allow you to build binary and text codecs. And the parsers that you can define using this little DSL, again, they have a lot of similar structure to an applicative, but you can't define an instance. And that's because these instances, these type classes that we have, they're just too limited. They're too narrow. They're too fixed, too rigid. We can't describe the structure of things like this using them. And you may have, if you've been functional programming for some period of time, you've probably heard that applicative structures can be introspected and monadic structures cannot be. So that's one reason to use free applicative instead of free monad. But this turns out to only be true if you're talking about the monad type class. So if you're talking about the more generalized notion of a monad, in category theory, there actually are introspectable monads. And they're lawful, they satisfy all the laws. Like, you can actually define such a thing, and that allows you to build parsers and other types of things that can be branching. We can't write those.
John, I think we've lost you. Can everyone else hear me?
Yep.
Yes.
I can hear you, but I can hear you.
Yep. Okay, good. We'll just wait for John to return. It's probably his internet connection.
Yeah, same problem here. John frozen.
Yeah, John seems to be the only one affected. Sorry for all the glitches to tonight's event. It is 2020, so you should be used to it.
Yeah. We are.
I'll get used to 2020 when it's 2021.
Well, we can always blame certain people.
I'm kind of waiting for 2021 to be about us having to wear 2 masks instead of 1, yeah? Let's see. Good stuff. Thank you all for your patience. Thank you all for your patience and the fact that we had to restart. Yeah, John is trying to redial now. Whilst we're waiting, is anyone planning to attend the Haskell Love conference this weekend? I believe it's this weekend, if I'm not mistaken, right?
Yeah, it is this weekend. Although one thing that's interesting is on Friday it's in European Standard Time, and then on Saturday it's on East Coast time.
Okay, so, interesting.
Just something to keep in mind. So at least for me, like on Friday it starts at 1 in the morning, which is a bit early.
Yeah, that's good to know.
In my time zone, it starts today. I'm in Australia, and starts this evening. I'm hoping to attend some talks.
Thanks for joining us from Australia. Thank you.
I used to live in San Francisco. Then I attended the meetups in person, but it's actually nice for me that I can attend remotely this time.
Yeah, the nice thing about it is the fact that we're getting a lot more international crowd joining us, and also international speakers. Last meetup we had a speaker from doing the talk from Singapore, and then of course Pierre. I don't know if he's online right now. He did it from South Korea a couple of months back. I know he's trying to dial back in, John. He's just, I think, internet issues. Whilst we're waiting, any particular topics on Scala everyone would like me to find a speaker to do a talk for? Is there anything that you feel that we haven't had any meetup or content over? Here comes John. Welcome back, John. Are you there?
Thank you. I had to restart my router, this house's router. I apologize for the technical difficulties.
No problem at all.
So where did everyone lose me?
You stopped at config.
Alrighty.
Do you want to share your slides again?
Yes. Okay. So config.
Yep.
All right. So let me pick up here. So Zeo config, it has this structure that is applicative-like, but cannot be described by an applicative. And in a similar fashion, Zeo codec, it has structure similar to an applicative, but it can't be described by these type classes. And if you're a functional programmer, you've probably heard that applicatives can be introspected and monads cannot. In fact, this is only true if we're talking about the FP library's definition of monads. For the category theory definition of monads, actually there are restricted types of monads that we can look at and we can introspect. And using this type of introspectable monad, you could build branching parsers that you can fully optimize in advance, and branching analytic pipelines that you have full transparency into, and you can do whole pipeline optimization on, and other types of very interesting things. So we're not doing this. We're not building these libraries, and in my view, partially it's because we can only see the world through these functional programmers. We can only see the world through the type classes that we have, and that lack of imagination basically prevents us from building other incredibly useful and incredibly powerful data types equipped with operations that would allow us to solve problems in new and very important, very practical, pragmatic ways. Another interesting case where this problem rears its head is sometimes you want to build a DSL using a data type that satisfies that would almost be a functor, but you want to restrict the types. An example would be RPC. So you're doing remote procedure calls, or maybe an analytics engine where you want to be able to say you can map to any type that can be serialized. You can't map to any type. You can only map, for example, this Spark RDD to another data type for which there exists some sort of codec that allows us to do long-term persistence. You want to do that in event sourcing and in certain analytics problems and in lots of other places you want to do that. You can't do that. And the reason why is Functor doesn't allow you to. Functor has no ability to constrain the target type that you're mapping to. And as a result, you can't build little languages like that that form a valid functor. And as a result, no one is doing it, by and large. Another interesting pain is not caused by that. It's actually caused by the fact that when these Haskell abstractions were ported over into Scala, the choice was made to not use variance. And unfortunately, that means that some problems that the Scala compiler can theoretically solve are not solved automatically for you by the Scala compiler. You have to solve them manually by calling functions. An example of this is, let's say you have something that is a functor, like an option or a future or something, and it contains a dog. If you're interacting with this data type through its functor interface, then if you try to take this dog value and assign it to something that's typed as an animal, so you're trying to widen that type. Every dog is an animal, and you're trying to widen an f of a dog into an f of animal. Then Scala doesn't let you do that. Instead, you have to call this method on these functor type classes called widen that allows you to do this. But the interesting thing about this is everything which is a covariant endofunctor in Scala can, in theory, support this auto widening for free. You shouldn't have to do this. Scala should be able to take its subtyping judgment on dog and animal and lift it up into work in the functor context. And it can actually. Scala is powerful enough to do that, but you have to be committed to using declaration site variance in Scala. You have to be committed to embracing Scala's subtyping, not just its functional parts. And to date, these functional programming libraries have eschewed subtyping and have made all of their type classes, almost all of their type classes, totally invariant in all of their type parameters, which causes massive pain for end users of these libraries, leading to very poor ergonomics. Another problem is that libraries like Scalaz, they import wholesale Haskell's laziness, which turns out to be a mistake. And then Cats, it goes the other way, and it imports Scala's strictness into the FP libraries. And that doesn't make any sense at all, because when you're talking about the functor hierarchy, you're talking about a realm in which you're using DSLs to describe some type of effect, whether that's effective optionality or non-determinism or input-output asynchronicity or whatever it is, concurrency. You're building little DSLs. All functors describe a DSL with a mapping operation, and you can build other operations on there as you explore the functor hierarchy. And once you get to applicative and beyond, you can build values that describe processes that go on forever. And as a result, any sort of type class that works on functors, so anything that defines a binary operator on functor, it needs to be lazy in all of its parameters. That's the only way that makes sense. And that's a design decision not taken by Cats that should be taken. And Scalaz goes the other way and makes everything lazy, even things that don't necessarily make sense. And so that we have no library in the middle that basically recognizes the importance of laziness as applied to effects and strictness when applied to data structures. Also, we have an issue with lawless type classes and operations. So we have a bunch of type classes and operations defined on them that have no laws, and there's no way of creating generic code that is known to be correct by using these type classes. This is a problem that Haskell has, as well as the FP libraries in Scala. And then also we have type class proliferation. So take a look at all the different type classes here. Dozens and dozens of type classes, and these are the ones in Cats. Okay, if you go to Scalaz, you're probably looking at 2 or 3 pages of this. And you can see that there's a lot of similarities between a lot of these different type classes. Like we have commutative applicative and ordinary applicative, and we have contravariant monoidal, and we have monoidal and invariant monoidal, and so forth. It's almost like someone took a bunch of adjectives and combined them all together in these semi-random ways and generated this massive sort of sprawling hierarchy and took a subset of that and dumped it into the library. There's a lot of stuff here. And the reality is most people don't know what these, even most functional programmers, they don't know what these things are here for. what problems they solve, or why there are so many of them, or why there are some variations and not other variations. It's just randomness. It's ad hoc chaos. And people take a look at this, if they're not from an FP background, and they say, this is not simple. Obviously, we like to say functional programming is simple. You know, we're functional programmers because, you know, we're too dumb to not be functional programmers. But you look at this, and there's no way in which you can conceive of this as being simple. There's a lot of complexity here, and there's a lot that you have to study and learn. And even once you study and learn it, you're still probably not going to remember all of these different type classes and all the laws and the relationship between all these type classes and what they're all for. That's just not going to happen. This is too big to be easy to store in your brain in a fashion that you can use on a daily basis. And then we come to another of my pet peeves here, which is monad transformers in Scala. And I'm not a fan of monad transformers in Scala. Actually, you can go to Haskell, in which monad transformers are 1,000 times easier to use. And you can find people who don't like monad transformers in Haskell. But if you go to Scala and you try to use monad transformers, well, let's just say everyone who went down that path, you know, eventually ends up going to Scala because it's just so incredibly painful. And the pains arise from multiple reasons, but one of them is just type inference on these types of structures does not work very well. Performance is really awful. It's really terrible. And some of these, a lot of them actually, a lot of these data types don't use declaration site variance, which makes it even harder to use. Actually, I remember teaching the state monad one time, and I remember, I know the state monad. I can write an index state monad for you. That's stack safe and all these other nice properties. I can do that in like 20 minutes. I was using one of the state monads from an existing library, and I couldn't remember the names of the methods, like were they put or put s? Was it get or get s? What are these things called? Where are they located? Like, why isn't this inferring? Why do I have to put the full type signature here? It was such a painful experience. I'm using that state monad, and I totally understand this thing. And you know, imagine if you're working with some monstrosity like this on a day-to-day basis. It's just not fun to be doing this, and there's no real reason. This is not giving you an advantage over imperative programming. This is not a strength of the Scala programming language or a strength of FP in Scala, in my opinion. Well, in response to all of that, I hope you're asking the question, is there another way that we could factor the type class hierarchies such that we could potentially solve some of these problems? Is there maybe another way we could look at things that we could gain more expressive power, but also radically simplify things to a level where it would be easy to teach? And could we actually embrace features of Scala and get this to a point where it could be fun, joyful to use? Could this be something that you get excited about using every day?
So we've seen that we've got some significant problems here. How do we start to take a step forward here in addressing these? Well, what we really try to do as we were in the process of developing Zeo Prelude is step back and think about what the most fundamental way of thinking about things is. And to us, that was really an algebra. And as we think about it, an algebra is a set of three things. It's a set of values, operations for combining those values, and laws that describe how those operations behave. And the great thing about this, the first great thing about it, is that it's something that everyone already knows. So a really simple example is you can think about addition. Addition forms an algebra. So our set there is integers. Our operation is just adding them. And there are a bunch of different laws, but one really, two straightforward ones we could say is it's associative. So doing x plus y plus z is the same as doing x plus y plus z, and it's commutative. So 1 plus 2 is the same as 2 plus 1. And the great thing about these algebras is you already do them all the time. If you're programming in Scala, every time you define a new type, every time you do case class X or trait Y, that's some set of elements. So every time you're doing that, you're doing the first part of that. And the odds are every time you're defining a data type, you're doing it so you can write some methods on it. And very commonly, you're going to have something that takes two of those and returns another one. Doesn't have to be. Could be that you have a unary operation. You have like negation for integers. Could be you have an operator that has 3 elements instead of 2, but combining 2 elements into 1 turns out to be really common. And if you can do that in a way that composes, you can end up combining 3 elements or 4 elements or an unlimited number of elements. And so there are lots of these different algebras. We're just going to go through a couple of examples here. So one would be something that's an associative operation. So we just saw that addition was one example of something that's associative, but there are lots of other associative operations that we could think about. Taking the maximum of values as associative, taking the minimum of values as associative. Another type of algebra we could think about is operations that have an identity element. So for addition, that identity element could be 0. For multiplication, it would be 1. For combining sets with, it could be the empty set. And again, there's just a law here that's pretty simple that just says that using this operation, combining any value with the identity element gives you back that value. Another simple one would be that commutativity property we talked about, that doing x plus y is the same as y plus x. And so these are examples of algebras, but one of the really nice things about thinking about them this way is that there are other algebras that we can define. We could think about an algebra for operations that are idempotent, that doing it twice is the same as doing it once. And that might be valuable for us in some context. And we can also combine these together in different ways. So we can say that we need an operation that both has an identity element and that is associative. And this, in a way, is much more compositional than the category theory-led approach we've had before, where that, in a sense, requires us to privilege certain combinations of these properties that we say, okay, this monoid thing is important and it has associative operation, identity element, but then we suddenly need to remember, okay, we've got a monoid, we've got a group, we've got an abelian group, and what extends which, and exactly which properties do they have, versus just saying we have these set of algebras and we could combine them in different ways to have things that have the properties we need for what we're doing. And the other great thing about these is that they're everywhere. There are a ton of them that exist on any type you could think of in the Scala standard library, addition, string concatenation, more complex types, like you could think about merging streams as being an operation, as well as all sorts of types that are specific to your own business domain. So you could think about if you have 2 CSV files, you could combine them in a way that it's probably associative, that adding 1 and then a second or a third, whatever order you do that is the same. You could have an empty CSV files, an identity element there. Seems like that's not a commutative operation, that which order you combine them determines which order the records are. And that's the kind of thinking that even if you didn't have formalized in that way, you probably think about yourself and implementing these methods and thinking about what properties they should have and what's valid to do with them or not valid to do with them. So this gives us really the basis then for what we're going to talk about now, the actual code of how we translate this to Zeo Prelude.
So Zeo Prelude, what is Zeo Prelude? Well, it's a small little library that's trying to bring common, useful algebraic abstractions and data types to Scala developers. And really, it's an alternative to Scalaz and Cats that is based on very radical ideas, very radical ideas. And they really embrace the modularity and the subtyping in Scala to offer 2 things. Number 1, new levels of power. you can talk about the structure of data types that you cannot talk about using the classic functor hierarchy. And number two, ergonomics. Now this is designed to fit well into the Scala programming language, to embrace subtyping, not just the functional side of Scala, but also the object-oriented side as well. Basically, to take the Zeo design philosophy and push it into the space of functional programming abstractions. The guiding design principles behind here are, first off, radical. So basically ignore all dogma. It doesn't matter if 100 people say to do it one way. Well, that's not a reason for doing it. Number two, orthogonality. So you probably got the sense from looking at all these different type classes, me describing duplication, that maybe these type classes are not orthogonal. Maybe there's some overlap between them. And the goal for Zeo Prelude is have no overlap. Type classes should do one thing and do it well, to the extent that that doesn't interfere with ergonomics. Be principled. So have type classes that have laws that can be checked. Be pragmatic. And that means if you have data types that don't satisfy laws, but that are still useful to use in most cases with these instances, then provide them. For example, double and int. These don't satisfy any useful laws almost. However, it turns out that we know about the limitations of these data types, and we want to be able to use them in generic code. So we go ahead and provide those instances for you. Scala first, which means embracing subtyping. And that means embracing subtyping even if there are limitations or drawbacks today. So rather than, this is a pet peeve of mine, rather than sit around on the sidelines and complaining that Scala has bugs here or there, what we as the functional programming community should be doing is rolling up our sleeves, finding those bugs, reporting them, and fixing them if necessary in order to move the whole Scala community forward. I think that's the best philosophy. For a long time, functional programmers avoided lots of features in Scala, and I don't think that makes a better Scala. It doesn't make a better future for everyone. We need to be embracing all of Scala and finding and fixing bugs, if necessary, ourselves in order to make forward progress. Minimal. So coming up with a set of type classes that allows us to describe a huge amount of variation, but in a small package, and not trying to do esoteric things that are 1% cases. So if a use case is required by 90% of people doing functional Scala, then yes, include it. If it's required by 2%, definitely don't include it. Accessible, which means that to the extent possible, things should have good names, good documentation, and infer well, and fit.
John, we've lost you again. I need to find a way of coming up with some background waiting music for Google Meet. Thanks for patience, everyone. I'm sure he'll be back shortly.
Well played. Well played.
Okay, who's trying to give me anxiety attacks here?
Is that jazz? Play the right note already. Am I right? Come on.
Who is that out of interest?
I don't know.
Oh, it's Jeremy, our very own Jeremy. Jeremy, by the way, I'm still waiting for you to do a talk at SF Scala.
Someday I'll do it.
How does September sound to you, Jeremy? Okay, we're back with John.
Where did I lose you? Here?
Here.
Yep.
Okay, which one?
Opinionated.
Opinionated. Okay, it's okay to be opinionated. So Zeo Prelude has 3 areas of focus. Almost everything in Zeo Prelude falls into one of these 3 buckets. First off, data structures and patterns for traversing them. Patterns of composition for types. So this is taking 2 A's and combining them into another A. And then patterns of composition for type constructors. So taking an F of an A and another F of an A or an F of a B and combining them together into another F. So that's like taking 2 futures and combining them into one. So one of the major troubles with the functor hierarchy, why it's not very expressive, is basically everything after functor. So functor is fine by itself, but then everything else that builds on functor, it starts to go down a specific path. And this is a very anti-modular path that results in the lack of expressivity that I've previously talked about. It's like the functor hierarchy is taking a notion of Scala function. Actually, it's an arrow in category theory, but think of it as a function. It's taking the Scala function and it's conflating that exact structure of that function into all of the operators that compose these things together. So you have these 2 things and they're all tangled together inside the functor hierarchy. Now, let me show you that in the case of monad. So monad looks like this, as Adam introduced. It has this map and app and pure and flat map. And I want you to look and see the number of places where you can see a Scala function. You can see it in map. We really can't get away from that. For this specific type of, for a monad, we need something like that. We need that to appear in some concept of this endofunctor in Scala. Then we have app, which also, inside there, you can also see another Scala function, the A to B. And then inside pure, it's a little less obvious. But if you decompose pure into map and a simpler value, then you can see that there's another Scala function embedded inside there. And then finally, there's another Scala function embedded in flat map. So this definition of monad is taking what a Scala function is, this A to B thing. It doesn't, in category theory, it doesn't have to be a function A to B. It could be something else. Anyway, it's taking this thing and it's embedding it into every single operation. It's conflating 2 things. And what Zeo Prelude is trying to do is detangle them. And so to detangle these things, one of the things we could do is explore an alternate encoding of monad. And in this encoding of monad, we have a map operation that mentions this Scala function. But that's it. We have a zip operation that zips 2 F's together and gives us back a tuple, but has no Scala function in it. We have an any value, which is just a simple value. It's an F of any that satisfies certain properties when composed with the other ones. You can reconstruct pure or point or return from that and map. And then we have flatten, which takes an F of an A and flattens it out to an F of an A. So this space is here. This is orthogonal. There's no conflation of concerns here. We've detangled everything. And this turns out to be key to unlocking the design of Zeo Prelude. So detangling the functions, the arrows in these categories from the composition of these values that have this structure is the critical breakthrough on which Zeo Prelude is founded. This and taking advantage of Scala's support for subtyping that allows us to take modular units and combine them together to get something that has all of their pieces. So it turns out that If you pull the functions apart from the composition, then you can decompose huge numbers of the type classes that you saw on the preceding screen and many others in terms of way simpler building blocks. And I'm going to give you a small taste of that over the coming slides. I don't expect anyone to follow along with this. We haven't introduced these building blocks, these pieces, but just take a look at the sheer number of type classes that you can break down into smaller orthogonal parts. So we can describe semigroup, commutative semigroup, monoid, commutative monoid group, abelian group, with a small number of type classes and many others besides. In addition, we can define functor, contravariant, invariant, alternative, and invariant alt with just a small number of different type classes. You're going to see them again on the next slide, all composed together in different ways using Scala's intersection types. We can also define, using these same small number of type classes, invariant semigroupal, contravariant semigroupal, semigroup K, monoid K, contravariant monoidal, invariant monoidal, all with these same type classes. And not only that, but we can also describe flat map, monad, divide, divisible, decidable, apply, applicative, invariant applicative, and lots of type classes that no one has ever bothered to create. They may not even know they exist, but they do exist, or at least in theory, things exist that have these types of structures. We can describe them merely by composing together these simple orthogonal building blocks. This is a whole new level of composability. This is composability at the level of type classes. Simple building blocks, which can be used to solve a huge number of problems. So what do these look like? Well, Adam?
Thanks, John. So as we said before, one of the building blocks of Zeo Prelude is ways of combining types. So some of these you're going to find really familiar because they're the exact same algebras we talked about earlier. So we have this type class associative that just describes an associative operation. And just like we talked about, the law for that is that we get to move those arrows around. We get to combine the first thing and then combine the second and the third, or we get to combine the first and the second and then the third. And that's it. That's just one algebra that we can have here. Then we can build on that and we can say, well, we could have an associative operation that also has an identity element with respect to that associative operation. So now when we combine when we use that combine operation with any value in the identity element, we get back that same value, whether we do it on the left or the right. We can also have an operation that, in addition to being associative, is commutative, where we do X together with Y, that's the same as doing Y together with X. And we can pick which combination of those we require for whatever we're doing. So we could require an operation that's commutative, associative, and has an identity element, or we could require the one that meets our needs. And that's how essentially with these three type classes, we're able to replicate all those different combinations that you saw above. So then we go from there to the operations that allow us to describe transforming values within some type constructor. And so this is the function or the arrow part of what John was talking about. And so the first one we have is this one covariant that defines in a way what would be the kind of traditional understanding of functor here, where you're going to change the function that we're going to apply here is just something that takes an A value and transforms it to something that is any B value at all, completely unconstrained. So that's the operation we could have on list or future or option that we're familiar with. But we can also, and one of the great things with this is it's got the variance attached to it. So unlike the examples we saw before, now we're able to lift that natural subtyping relationship from values to this type itself, where just the fact that we have this function f a to b means that we can always widen the type, because we could always just map the identity function widening the type. But when we didn't have that variance annotation here, we had to manually use that widen operation to do that. Whereas now that'll happen naturally for us. We can also define a contravariant type class here that has essentially the same type signature, except you can just see that the f looks different. Instead of being a function a to b being lifted to a function f of a to f of b, it's now a function b to a being lifted to a function f of a to f of b. And again, through the use of variance here, this now automatically allows narrowing the type of that. And what gets more interesting is we can also start to add new ways of mapping here. So we have this invariant type class that allows mapping, but this time with this case class essentially represents an equivalence that now has a function from A to B and a function from B to A. And now this says we can lift an equivalence from A to B to go from an f of A to an f of B. And you can also imagine here having other ways of transforming values in context, other ways of doing that function or arrow part that are constrained in some way, that only allow that operation to be done when there's some type class that exists for B. Only a subset of B values you can map to, supporting some of those use cases for constrained DSLs we talked about before. And all of this takes place within this set of type classes that describe that arrow, that function composition, separate from describing how to combine individual values. And then we can put those together for our types. So then the next set of type classes we get to essentially describe those same operations of associative operations, operations of identity element, commutative operations, but at the level of type constructors instead of at the level of values themselves. And with this, for each of these, I'll illustrate an example from Zeo for those who are familiar with it. So you can see that there's, well, now we're adding some Fs, there's nothing exotic here. These are all operations that you already know about. So the first one is these associative operations. And for all of these operations, we're going to see that there's what we call a both and an either variant here, because we're doing this at the level of having, instead of just two FAs and being able to combine them, we're doing it at the level of having an FA and an FB. And so without knowing anything else about what those A's and B's are, conceptually, there are really two values, two ways we could combine them. We could either say, I want both of them, or I want either one or the other. So the first operation we have here is associative both, which is going to take two values FA and FB and just give us a tuple of FA, FB. And so that's essentially the zip operation. So if you think about, like from Zeo, that's taking two effects and running one, then running the other and combining their values. And then from that, we could get to other operations like zip with that we know about by combining having this associative both with something like covariant that we talked about before. But by combining those individually and building them up, we give ourselves that modularity and the ability to say, maybe it's not, it doesn't have the full power of being covariant. Maybe it only works for an invariant type. Maybe it has other constraints on it. The next type we have here is the associative either instance. So this is an associative operation that says, well, give me either A or B. And so a simple example of that from Zeo you could think about is this or else either operator, which says run this first effect, and if it succeeds, give me its value. But if it fails, then run this other effect. And we can see how this is associative, where if we have Zeo 1 or else either Zeo 2 or else either Zeo 3, whatever way we arrange the parentheses, we're going to keep running them from left to right until we get the first one that's a success. From there, we have one more associative instance that's interesting to us. And this one requires a little bit of squinting, but this one's called associative flatten. And this says that if we have nested values, that operation of flattening them is itself associative. So a simple way to think about this would be if you have a list of lists of lists. So you have 3 layers nested of lists, whether you take those 2 outer layers and you flatten them first, and then you flatten that with the innermost layer, or you take the 2 inner layers and you flatten those together, and then you flatten those with the outermost layer. Either way, you're going to get the same elements. So that operation of flattening is itself associative. And an example of that would be flatten on Zeo, as well as flatten on a lot of other types like lists. So then we start to add more structure to this, and we can say that those operations themselves have identity elements. So we said associative both before is going to take those 2 FA value, an FA value and an FB value, and combine them into a tuple. We're now adding this additional any value here that essentially is a identity element for this, that is a value that is going to leave the other value unchanged, is going to not add any new information. So here, again, we said that zip was the operation that combines them, and this any value in this case is just the unit value for Zeo. It's just going to return a successful effect that has the unit value in it. And so we can always take any value and combine it with the unit value to get back a tuple that we can vacuously discard the unit value to get back the original value. And that's always going to give us that value unchanged. We can also look at there being an identity element for that either operator. So here we said that the way of combining them was this or else either, that essentially takes the first successful value, and if the left value is a failure, tries to run the right value. And here the identity value would be this what we call halt with an empty cause, which essentially says this is an effect that fails with an error that contains no information. So we can see that combining a failed effect with a successful effect is always going to give you back the successful effect. And then we need this cause.empty thing because Zeo does a little bit of additional information preservation of preserving the errors on both causes if they both fail. So we have this cause.empty thing that essentially says this is a failure that contains no information. So again, we're able to combine these 2 things, and we always get back the other one if one of them is this Zeo.halt. That's an identity value for that operation. We can also think about having identity operation for that flatten. And again, it's the same thing of typically it's that Zeo.unit. And we can think about the law here being that if we use Zeo.unit and we use map to put the value into that, we can always use that to essentially add a layer of F. So if I've got an FA, I can always use those 2 to make it an FFA or a FFFA. And so I can always vacuously add a layer through that, and then I can flatten it back and I get the same thing. So you can think about like if I have a list and I just put another list constructor around it, and then I flatten the whole thing, I just get back my original list. We can also talk about commutative operations. So particularly on these higher kind of types, these commutative operations often end up describing operations that have some level of parallelism and concurrency. So before we said that that associative both, that was going to combine an A and a B into a tuple, that was zip. That's not a commutative operation because that depends on the order of saying effect 1, zip effect 2 means run the first effect, then when it's done, run the second effect. So that's going to be different than run the second effect, then run the first effect, because we might say, you know, print Adam, then print Fraser. That's not the same as print Fraser, print Adam. But this zip par operator is going to run 2 effects in parallel and return their results. And so whether we run A and B in parallel or B and A in parallel, it's the same thing. We can also think about a commutative interpretation of that either operator. So in this case, it would be the race operator for Zeo, in particular this race either, that says, run these two effects and return the first one that completes, and give me that in an either, telling me whether it was the left or the right side that was the first one to complete. And we can see that when we race two things, whether we race A and B or race B and A, both times we're starting them at the same time and we're taking whichever one is the first one to complete. So there's no difference between those two. That's a commutative operation. And then finally, we talked about, so we had ways of combining values, we had ways of combining type constructors, and then we have ways of traversing data structures. And we have this traversable type class that lets you describe having some collection type and applying a effect, a function that's going to return a result in an effect, and getting back a new effect that's going to contain that data. And while there's type signatures and constraints on it, when you actually use it, it's very straightforward. It looks like very simple Scala. You have this type of syntax you can write where you just say, for each request, handle the request. And that handle request may contain a Zeo effect. It may contain some other type of request. And it's just going to apply that to each element of that structure and wrap that all up in one effect. And then from there, we can further specialize to this non-empty traversable, which gives us this for each one operator that has a very similar signature, but both has fewer constraints on the types we have to have, as well as provides us access to some additional operations. So if we know the structure is non-empty, we can reduce it without having to provide a zero element, versus if it could be empty, we would need to fold over it and provide a zero element. And then we've got another set of type classes that help us out with various things. We've got debug, which is like show, you might know from some other functional programming libraries, that says, given an A, here's a way to represent this in a way that could be rendered. Equal, that gives you a way to compare two values for equality. Hash, that gives you a way to return a hash code for a value. Or, that gives you a way to order two values. And the great thing about all these is they embrace that declaration site variance. So all of these fundamentally are functions that take in one or two A values and give you back something else, whether it's a Boolean or an integer hash code or an ordering. And so all of them are fundamentally contravariant. They can assume A values. And by embracing that aspect of Scala and actually putting that variance there, now a lot of things work much more naturally, where if we have a way of ordering any animal, then that means I definitely have a way of ordering dogs. I can order dogs, I can order fish, I can order cats, I can order any animal. Versus in other encodings where this was invariant, if we had this, we'd get errors when we tried to apply this to types that weren't the specific type we were looking for. We've also got a set of data types that we've included here. And the main difference in the approach here is we've really tried to embrace Scala, embrace the Scala standard library and the types there. So we have a non-empty list type, but it actually, it just having a ton of methods implemented on it itself, it's automatically convertible to a Scala list from the standard library. So if there's any method that's not defined on it, it's available on a list, you'll get it there. If you're trying to pass it to some method that's expecting a collection, that will work for you. So trying to be very ergonomic there. We've got a validation data type. So this will allow you to accumulate multiple errors. Unlike some, it's not, some other validation types are parameterized on the data type that's used to collect the errors, which can create issues when you just want to go use it, because typically you just want to accumulate your errors. You don't necessarily care that much about exactly what data type you're using, and it can create inference issues. We bake all that in for you, so that's just ready to go. We've got another one called ZSet that's essentially a more polymorphic set that lets you, it's parameterized on some notion of how many values are in the set. So It could be a set where the measure is just Booleans. That's a traditional set. It could be a multi-set that captures how many of an element is in the set. It could be some type of fuzzy set. So that's something else interesting there. And then we've also got a fun solution for monad transformers. So in case you thought that Zeo was great, but just didn't have enough type parameters, we've got this data type called Z pure that represents a computation that takes in some initial state and outputs some state while also taking potentially an environment and producing either a value or failing with an error. And this is essentially the solution to monad transformers. And it's really taking a lot of the same ideas from Zeo and applying them to this problem, where one of the core ideas from Zeo was this concept of effect rotation, that instead of having layer on layer on layer on layer of monad transformer to kind of give you each capability and having all the issues associated with it, you have one data type that bakes in all of these capabilities, and then you can use the ones you need for a specific problem. So if all you want is state, that's fine. Then your in type and your out type for state is going to be the same. It's going to be that S type. You're not going to require any environment. You're not going to be able to fail, and you're going to return a value A. And that's going to perfectly describe the state type and give you great performance for that, but also give you a lot of flexibility where maybe you say, hey, I want my state computation to be able to fail because I need to bail out early. Well, that's fine. So then you're going to have an error type there. Maybe you need context. Maybe you just want a reader. You could do that too. So you get a tremendous amount of flexibility there. And we'll see some of that in the next few slides. So you might say like, hey, that's still a lot of type parameters. Seems like a lot. Here's the alternative. Here's that same set of capabilities built up using traditional monad transformers. So you need a Kleisli here of an either T, of an index state T with an eval inside it for stack safety. And you need multiple type lambdas because every one of these monad transformers is expecting something that only has a single type parameter, but none of these things actually do. And boy, this seems like not very fun to write. And I had to experience some of this actually because I went to go and benchmark the implementation of Zpure with a monad transformer stack. And just writing the code to do the benchmarks ended up being quite painful because one of the problems with these monad transformer stacks is you can describe this whole type, but the type isn't any actual data type that knows what it is. So I've got this Kleisli of either T of state T thing, but then I want to just implement a simple constructor that's going to get the current state. Well, the data type I have is actually just this Kleisli, which the Kleisli doesn't know anything about the fact that 2 layers of type constructors down, there's a state monad there. So when I try to do this get method, it doesn't exist. I've got to like define 2 different sets of type aliases just to avoid having to do more type lambdas. And then I have to do these multiple lift Fs where I have to specify the type parameters just to get this really simple constructor that literally all I'm trying to do is get the state here. And then also just like writing the signature, I know that I'm creating type inference issues for myself because all this constructor is supposed to be doing is getting the state. Well, why is it parameterized on a environment type or an error type? The reason is that the stack, all of these parameters are invariant. So I'd like to be able to say this can't fail at all, so the E is nothing, and it doesn't require any environment, so the R is any. But if all of these are invariant, then that's going to cause me a bunch of type inference issues, and I'm either going to need to manually narrow or widen. So I kind of have these extra type parameters floating around, so hopefully I can specify them if I need to, or maybe if I'm lucky, they're going to get inferred. On the other hand, if I'm working with Zpure, Zpure is just a simple data type that, yeah, it's got 5 type parameters, but it knows about all of its type parameters, and it's got methods implemented to deal with all of its type parameters. So getting the state with Zpure is just zpure.get. And to make it easy for you, we've got a type alias that type state equals Zpure, like we saw above. So literally all you do is you do state.get. And you don't even have to know that there's this more polymorphic thing you're working with. But all of that power, if you need it, is there, as well as the optimizations that went into it. Because this Zpure type was built using a runtime that was adapted from the Zeo runtime, and it's very optimized. So here's a comparison of doing simple operations of traversing a data type, doing repeated get sets, repeated left associated binds, with that monad transformer stack we looked at before versus Zpure. And Zpure is between 10 and 30 times faster here. And that actually makes a big difference, because for these types of operations, you know, maybe if you're working with effects, you can say, look, if I'm doing database IO, the fact that my flat maps take more or less time with one effect system or another, maybe that's not actually going to drive the performance of my application. But you're using state if you're using a traversal to do just like zip with index or fold left in terms of the default implementation for fold left on a traversable, or what would be called the traverse type class in another functional programming library. That's done in terms of that state monad. So that's actually a huge performance implication. And even if you say, well, you know what, Adam, like this wasn't a fair comparison, like I don't need all that power in Zpure, all I need is state. Even if I do the same benchmark with just a state type from another functional programming library that just has that state and that eval monad layers, doesn't have any of the others, I'm still going to be between 3 and 10 times slower. The final thing we've got for you is new types built in. So new types is, I think, another one of those things that's always been a really nice idea from functional programming libraries, but at least for me, always seemed like not quite ergonomic enough to really use day to day. And I think we've got some really nice ergonomics for this, where it actually seems quite natural and is quite powerful. And all of this is done in a way where it's entirely at compile time and it's entirely plain Scala. There's no macros, there's no funny business like that going on, and there's no actual new data types or type constructors being created, all at compile time. And we've also got a bunch of really, really great options to let you solve different types of problems. So the first thing you'll see here is we've got both the ability to do what we call new types, as well as the ability to do what we call subtypes. So in this first example, we've got this object meter extends subtype of int. And so what this means is that meter to the Scala compiler is going to be a distinct type from int, but it's also going to be a subtype of int, even though technically we know there's no way to actually extend int to the compiler. This would be a subtype of int. And that can really be nice because it means that all the methods that we have on int exist on meter. So it can avoid a lot of boilerplate for us in implementing these, as well as any type class instances that exist for int are going to be in scope for meters. So we don't need to re-implement addition and multiplication for meters just to be able to work with them. We also have this set of constructors that have a subtype or new type F. And this lets you describe new types that are parameterized on some other type. So for example, we might want to use this sum to distinguish addition versus multiplication. If something has a sum, then we want the type class instance for associative to be adding it, versus if it has product, we want it to be multiplying it. but we don't really want to have to do that separately for integers and doubles and floats and every possible value we could add or multiply. So instead, this lets us define it at the level of a type constructor, where this just takes any type A and can return a sum of A. And again, if we want to, we can specify that this is going to be a subtype versus a new type. Finally, we have the ability to do smart constructors. So if I want to define a data type for the natural numbers, instead of using new type, I can use this new type smart. So this is going to create some type where the underlying representation is an integer, but the compiler is going to treat it as a separate type. And in this case, I want to treat it as a new type instead of a subtype, because I don't want some of the operations available on integers to be available on natural numbers. I only want to define the ones that are going to be valid on natural numbers. And the other thing that this comes with is built-in validation for this data type. So this is powered by assertions from Zeo test. And here I'm defining, here's the condition that a valid instance when I create it has to satisfy. This is greater than or equal to 0. And we've got a bunch of ways built in then to build these values that have that built-in validation as well as built-in error reporting. And this gives really nice ergonomics. So here's just a simple example, but one of the classic problems with all these functional programming libraries is you want to add a list of numbers versus multiply a list of numbers. And how do you do that? And how do you do that with some type of new typing mechanism? And with Zeo Prelude, it ends up being really nice because of that subtyping mechanism, where essentially we're just taking this list and we're mapping the values to this new type using either this sum or product constructor, but then we don't even need to do anything to unwrap the values again, because sum of int is already a subtype of int. So the compiler can just lift that right back up to an int for us. So it creates a really nice ergonomics for working with these new types that is, I'm obviously a biased observer here, but I think better than anything we've seen before. With that, I will hand it back to you, John.
All right, so this is where Zeo Prelude is today. We've got that bundle of data types and type classes that are small. They're based on algebraic properties of associativity and commutativity and identity, and they're modular, so you can assemble very complex expressive combinations of all these type classes to generate new structures that you can't describe using the existing hierarchies. But where to from here? Well, we want to do documentation, lots of really beginner-friendly documentation and examples. We want more instances of these type classes for data types in the Scala standard library and in the Zeo library. We need to do more polishing, where we want to do some effect type classes for, in particular, to describe the data type Z pure as well as the Zeo data type. We want to do some more performance optimization and make sure that all the operations in there are stack safe. So non-toy implementations of different operations that we may have right there now. We want to provide automatic derivation of type class instances for any ADT. That'll utilize different mechanisms in Scala 2.x versus Dotty, Scala 3. And then finally, we want to make sure that we get feedback from real users, and because that's one of the things that I think made Zeo such a great library, is that we had not only all these great contributors implementing features and writing docs and so forth, but also we had a lot of users who gave us feedback, and we took that feedback to heart and we used it to make the product better. So that's what we need for Zeo Prelude, is lots of people putting this through its paces and making sure that we flesh out any edge cases, and we make sure type inference is really great and everything really fits together well. So before we open it up for questions and wrap up, I want to do a special round of thanks to the Spartan members who contributed to this project. They worked nights and weekends to add features and docs and typo fixes and all of the above to the library. Dayan, Sken, Manfred, Jorge, Phil, Kamal, and Maxim. Thank you all for your contributions. Zeo Prelude would not be where it is today without your help. And of course, thank you to Solar, my friend, who invited me to give this talk here with Adam. It has been a pleasure. So if you have any questions, we will go ahead and take those. Please do check out this repository at github.com, Zeo-Prelude. That is not operational tonight. And given our technical difficulties, it is likely that will not be operational until tomorrow. But tomorrow we will go ahead and open that up to the public. Also, if you like Zeo Prelude, then consider please becoming one of my patrons on Patreon, and you can follow along with new projects and get my my weekly lessons teaching functional programming and one-on-one mentorship. And then finally, please feel free to follow both myself and Adam on Twitter or LinkedIn, or I have a blog at dgoes.net, and you can find both of our content on the Zyverge website, so zyverge.com. That's my company. That's where Adam works. That's where we're building a whole company around functional programming in Scala, so please check that out. All right, so let's go ahead and open it up to questions.
Jeremy, did you say you want to go first?
I have a question. So you mentioned that earlier on, you mentioned that the functor definition in Cats and Scalaz was a small subset of the possible functors.
That's right.
I agree with, but I didn't see how what you talked about tonight addresses that. Can you give a little more insight into how we could make more arbitrary functors from Scala to other subcategories, or?
Yeah, that's a really excellent question. So remember back at the beginning, I said that the functor that we have in these type class libraries is just a dot in an ocean of possible functors. And part of the problem why we need so many type classes using the existing functor hierarchy is because it conflates that mapping function with all of the other operations, like combining two f's together, all the different ways you can combine two f's together. It's all wrapped up into one package. That means if you want an invariant applicative, for example, which I don't think that exists, but you can define it. It's valid, it's lawful, it really is a type of lax monoidal functor. You have to define an entirely new type class. And there's only going to be minimal differences between that and the other ones, but you still have to define it. Now, using Zeo Prelude, you can actually reuse associative both and associative or identity both and various other type classes. The only thing you would have to change is instead of using covariant, you would just use invariant. So you would mix in invariant with what other capabilities that you wanted, and you would have a composite type formed through intersection types that would represent that new thing. Also, if you wanted to define, for example, a DSL for data types, an applicative DSL for data types that can be serialized, then you would use associative both, maybe identity both, together with a type of mapping operation that only allows you to map to target types that support serialization. And in that way, you would be able to reuse all of the type classes inside Zeo Prelude, but maybe introduce one of your own. And actually, for that use case and many others, you don't have to. So we didn't talk about this covariant subset and contravariant subset type class that are baked into Zeo Prelude, that ordinary covariant and contravariant extend, but the capability to operate on subsets of types that satisfy particular requirements as defined by a set of type classes is already baked in. So ordinarily, you probably don't need to create new type classes, but the point is, if you ever have to create a new type class, because the Zeo Prelude type class hierarchy is so modular, you won't have to reinvent everything. You might just have to create one new type class, and you can mix that in with all these other type classes and reuse a lot of the generic machinery. By the way, I don't think there is a full solution to that problem. And the reason is, in order to model category theory in its full generality, you need a much more powerful programming language, one that doesn't infer. You need something like Idris or Coq or Agda, and you need to be able to describe things that can no longer infer. I don't think that's worthwhile, honestly. I think you can get the vast majority of use cases from the combination of modularity and then subsetting on types. And that's what Zeo Prelude gives you, is it gives you the ability to describe all these new types of things you couldn't before, but without a dependently typed programming language and very complicated machinery that would not infer anymore. Excellent question.
Yeah, I think you're right. As a follow-up question, are you planning to open source this Zeo Prelude right now, or?
Tomorrow. I was planning on doing it tonight, but honestly, it's gotten so late with the technical difficulties and everything. Probably defer that to the morning. But yes, tomorrow it's going to be out there. It's going to be open source, and we're going to create a bunch of tickets out there for people who are eager to give a hand with the sort of last mile that has to be done in order for us to release 1.0. But unlike Zeo, this is not uncharted territory, so it's not going to be 3 years. It's more like 3 months or maybe even 3 weeks, who knows? But I think we're actually reasonably close to a 1.0 release on this.
Okay, so so many questions, but one more follow-up question. That a lot of the innovations here were variance-based. Why do you think nobody else that's traversed this territory, no pun intended, has attempted to use the obvious variances that should be applied to these different types?
Yeah, so I think that's a good question, and I think that first off, you do have examples of people who have created a more faithful representation of abstractions in category theory in both Scala and Haskell. So you have those people who have gone like just totally crazy with very fancy techniques. Ed Komet, for example, and a friend of mine, Alex, and lots of other people have created much more faithful representations of category theory abstractions inside Haskell and Scala. But those have not been very usable or practical. And conversely, I think that you've had people play around, like in my previous work with Red Eyes, and I know Michael Pokless did some stuff with Kodak, that were like skirting on the edges of this and saying, hey, there's stuff here. There's stuff here that's unexplored that we would like to be able to write type classes for that's very similar to what we have. We don't have that. Do we create ad hoc classes? What's not been done is the modularization of the type class hierarchy. That's chopping it apart into pieces. And that requires, first off, it requires compromises, because you have to decide what you're willing to give up. And that's tricky. And I think it requires time to figure that out. Also, it requires knowing deeply Scala and embracing subtyping, as well as knowing functional programming very deeply. And the subset of people who know and embrace subtyping in Scala and who know and embrace, functional programming is not that big. There's not gobs of people running in there doing lots of experiments. So I think the fact that you have to know a lot about Scala and subtyping and FP, and also you have to have played around with different variations of the classic hierarchy, has mean we've not seen a lot of innovation in this space. But I think now is a really good time in the period of functional programming in Scala, because people are starting to get more comfortable moving away from what Haskell did. For a while, that was considered the gold standard, and you didn't deviate from what Haskell did, because that's what it meant to do statically typed FP. But I think increasingly Scala programmers are becoming less afraid to just chart new territory and say, no, that made sense in Scala, it does, or in Haskell, it doesn't necessarily make sense in Scala, and there's no reason why we have to do something the exact same way that they chose to do it in that other programming language.
So you might say subtyping is considered an evil.
Yes.
As far as classes are concerned, but it is a feature of Scala that doesn't exist in Haskell. And when you
Yeah.
bring from Haskell, it might give a new dimension of how to define that thing in Scala way.
I absolutely think that subtyping here is a strength, and declaration side variance and the way it can be used to describe, well, lift up subtyping relations into these type classes and give you sort of automatically derived type class instances for things that are supertypes or subtypes is enormously powerful. And it's an example of playing to the strengths of the Scala programming language. And that's something that I know for sure I did not see early on. Doing FP in Scala, I avoided all the things that were not Haskell. And lots of other people did and still do that. They avoid anything that's not Haskell in Scala. I think that's the wrong approach. I think everyone who goes down that approach eventually ends up leaving Scala for Haskell, because you can't do good Haskell in Scala. You can't. Tony Morris is right about that. And if you want to do good Haskell in Scala, you'll end up dissatisfied and you'll leave. But if you chart new territory, if you find out how Scala wants to do functional programming, I think you can end up with something that is powerful in its own unique ways. It doesn't have the same strengths of Haskell. It has different strengths, but no less important for day-to-day programming. You can end up with something that's both principled and also joyful, because I think functional programming needs to be joyful. And the more we can do to make it fun to do FP in Scala, the more people will do it, and the longer it will stick, and the fewer people will leave Scala for Haskell. Great questions, really great questions.
Thanks.
Do you find what you're doing to be more mathematical? Because it seems that way. It seems simple and almost, I would hate to use the word elegant, but I'm just remembering how, you know, Cauchy sequences form a ring, and it sounds a lot like rings and groups to me.
Yes, so excellent question, Richard. I do believe that this is, even though it's a different approach from the classic functor hierarchy, and maybe doesn't use any of the category theory jargon or those type classes, it is more principled, it's more essential, because these operations, these type classes are more orthogonal. They actually themselves compose together in ways that you can't replicate. And also they're more faithful. That's what some people don't realize. They're more faithful to the original category theory abstractions, because how do we describe binary operators in math? We describe them by their properties. Associative, distributive, if we have two of them, or we have some identity, and so we describe them by their laws. And it's the same thing in Zeo Prelude. These operations, these binary operations, are described by their properties. You never have to wonder in Zeo Prelude what the laws are satisfied by an abstraction, because it's in the name. An associative both is associative for a tuple. Like, you don't have to remember. The structure is baked into the names. There's no more guessing. People know what the structure is from the names. And things like the associative both, for example, or rather the associative both and associative either, are a more faithful encoding of a lax monoidal functor than the applicative type class. The applicative type class is not anything in category theory. It's sort of a weird way that something in category theory can be used based on curried functions in Haskell. So I think it's, even though there's none of the category theory stuff in there, the essential structure of Zeo Prelude is more faithful to category theory, and it's also more principled, and it relates to the laws and more how we would talk about it from a mathematical perspective of binary operators satisfying these different properties.
Thank you.
Great question.
It's sort of what I'm thinking about. Also, the monad, I look at the monad as kind of an abstraction of a substructure in a program, and that it has this isolation effect and it has this predictive effect. And this seems to add to that capability of being able to predict from, I'm starting out here and I'm going to try to transition this thing, and it just feels cleaner. I don't know, that's just my thought about it.
I think it is cleaner, and what it allows you to do is to define new types of monads that can't be written using the standard monad type class. And I'm excited about that, actually. I think that people could now define generic type classes for parser combinator libraries and analytics libraries and so forth that use monads, restricted forms of monads, that allow you to do branching in ways that are still amenable to optimization.
I have a question. So when I was listening to it, I felt like, oh, okay, yeah, model theory is like getting into the discourse. And basically and the code is beautiful and the design is beautiful. But do you actually keep in mind like model theory and categorical like implementations, categorical models of theories, algebraic theories?
To some degree, I think that there's always going to be trade-offs that you have to make when you're trying to model super generic things in a programming language. And I think that these are not the only trade-offs that you could end up making. Also, there's parts of the class of abstractions that we've currently ignored, and that would include combinations of binary operators, for example, and lattices as a subset of those that we're not tackling right now. And maybe we'll tackle them at some point. For now, those parts have been left off, and we're focusing on the sort of 90%. And with a specific opinionated choice, that is not necessarily the only choice you could make. If you decide to branch off from the functor hierarchy, there's other ways you could go. This is one choice. It's one choice that I think that will be very useful, but it's still an approximation. It's not. I don't think there's a clean solution to everything out there that's also ergonomic.
Yeah, probably just not right now, but I'm working on that, so I'll send you a link.
Well, that's awesome. I hope to hear. I hope to hear more. Any other questions?
Yeah, John, this is Matthew Smedberg. Oh, sorry.
Hey.
So I posted it in the chat, but I kind of wanted to kind of tease out if this is more something that you think is useful for library designers, or more something that is going to be consumed by your workaday programmer. Because one of the things that I've had to deal with as I've kind of mentored younger programmers is, don't worry about all the type classes. Don't worry about all the complexity please don't import one thing from Cats and don't worry about it. Let the people who want the complexity deal with the complexity. So kind of where do you see this kind of adoption coming for Prelude?
Yeah, so great question. I think that functional type classes are useful to the advanced functional programmer. And they're useful in, assuming you're not doing something like tagless final, which forcibly introduces type classes into all your code, or not all of it, but a good chunk of it, then the uses of type classes are actually quite minimal. There may be, charitably, they're like 5% of your code base can benefit from type classes as an end user. So these are things that you don't need to use them. If you use them, you can eliminate some typing, basically, and some duplication, and benefit from generic functionality. But I think type class libraries are more obviously useful to the writers of libraries, and they can still be useful inside end-user applications for the common stuff. And by the common stuff, I mean combining data structures together. Okay, associatively combining data structures together, instant strings and maps and lists and vectors and trees, and just smashing stuff together. We all want that operator that just does the magically right thing in combining two things together. And that's a common use case, even in business logic. That's very common. And then the other thing that's very common in business code is this traversing the data structure and performing an effect for every value and collecting up the results. So that's the traversable type class. So those things, the associative combination of a value, and then the ability to traverse over a data structure and perform effects, that's in all applications. You don't have to use it, but it makes sense to use that. Concrete data types like validation, they're easy to teach, and there's uses in a lot of application for the concrete stuff. The more esoteric type classes, like associative combinations and identities and commutative combinations, those things are more useful for the library designer and the advanced functional programmer, and they're not going to be very pervasive in the typical application end user code base. But still, these type classes, they could enable new types of libraries, that because they'll be causing, I hope they'll be causing people to think about things that they weren't thinking about before, because they were viewing everything through that lens of Functor, Applicative, and Monoid. Yes, Jeremy.
Yes.
And then Michael.
So my last question, will Zeo come to implement these classes or provide a system, or is will Zeo Prelude?
Yeah, so excellent question. So the way that we're going about that is Zeo will remain dependency-free library. And that's because not everyone who is interested in Zeo is interested in functional programming. As weird as that sounds, that's actually true. Like, Zeo is just a great library for doing concurrency stuff. So you don't need to know anything about algebraic structure or anything to use Zeo. Just, use it. However, there will be some subset of Zeo users who want to talk about algebraic structure and benefit from generic code. And that subset, it's a good fit for Zeo, I think. And so Zeo Prelude is actually it already depends on Zeo, and it defines instances of all the type classes for all the Zeo data types. So if you want to use the Zeo data types in a generic context with generic code, or you want to do tagless final in Zeo, then I think Zeo Prelude is going to become an important ingredient for that. But you'll never have to depend on Zeo Prelude, because in my opinion, the audience for a library like Zeo is 100% of Scala users. The audience for a library like Zeo Prelude is maybe 10% or 5%. It's not as big. And it's for the reasons that everyone mentions. These type classes, when you're writing end user code, you don't need to use them. They make your life a little simpler. If you do, you can eliminate some duplication, but ultimately you could write that code yourself and just specialize it a bunch of times. Type classes eliminate that boilerplate, but you have to know about them, and know about them requires training. It's definitely inverted from the norm. And I actually think that kind of makes a lot of sense, because the foundation of everything is being able to model effects, like even to do a memo table, which is something that you would expect in an FP library. You have to talk about effect. Almost any interesting functionality is going to have to depend on that functional effect model. So I think that's the right way to model it, as opposed to the classic way of modeling it, which is to have the effect library depend on the FP library. I think that's actually backwards. Michael?
Believe that.
Yeah.
Finally?
I'm actually very interested. I mean, the design of the library is incredible. I think it's revolutionary. It's no longer a hierarchy, I believe. It's more called lattices. But I'm actually very, very curious about the design of Zepure, and especially you've added the state parameters, and it's actually a thing that could be embedded in the variance of the environment, like you did with Zeo, at least theoretically. So and also you've mentioned that the driver of Zepure is quite inspired by the driver of Zeo. So I don't actually understand the design of this Zepure. Is it an effect system? Is it only for synchronous data? What's the reasoning behind it? It seems to cross a lot the Zeo territory.
Yeah, I mean, I can try to hit on that. So I would think about Zepure as what you want when you want one of a constrained set of capabilities. So Zepure says you have the ability to access an environment, you have ability to change this specified state, you have the ability to fail, but beyond those things, you're not going to be doing any other effects. Right, you're not going to be forking fibers, you're not going to be doing network I/O, you're going to be doing these specific set of effects, versus Zeo is I/O. Zeo is you can do anything in the world within the context of Zeo. So it's for a more constrained set of use cases.
it's like a base for dimensional options, hiders, and all the stuff, all the classical stuff. Yeah. Okay. Thank you, got it.
Yep.
Nigel, Ben's got a question for you, John.
Yeah.
I see a lot of it's based on like associative, commutative, stuff like that, all the nice laws. However, we all know that there's no way to kind of enforce that in the Scala language. Is there like thoughts of creating something using Zeo tests to create kind of like a library similar to Cat's laws to verify that these things are actually working?
Yeah. So actually, I'll let Adam take this more on, but Zeo test has laws as a first class value, which is relatively new. And these laws can work on constrained data types. And so, Adam, why don't you talk more about the integration there between Zeo Prelude and Zeo test?
Yeah, definitely. It's been really nice being involved in both projects, and they've been useful cross-pollination for each other, because the need to test these laws and the desire to do so in a more polymorphic way actually led to the development of this functionality within Zeo test. And we think it gives a more powerful way to treat laws as values, because in other systems where you're testing laws, the laws actually don't have the full degree of polymorphism. The law is some method that says, well, if you give me a value, then I'll give you some test results. But in Zeo test, the law is actually a value itself that says, for any value that has these capabilities, I can give a test result. And there's a lot of neat ability to compose those together. If you add one law that requires one set of capabilities, another law with another set of capabilities, you get a new law set that's going to test all those laws and require all of those capabilities. And so that's actually been baked in directly into Zeo Prelude, where when you look at just about every data type, every one of these type classes, you'll see something like object equal extends lawful equal. And it actually gives you a very easy syntax of, you can just within Zeo test, you can now do check all laws equal. You just provide a generator for whatever concrete A type you want to check, and it'll do that for you.
Yeah, for law testing, I think that we've upped the game, basically, that there's just the laws, they're ordinary values, you compose them using plus operators, you check them in a way that's extraordinarily simple. Like, this is a level of ergonomics that I think we've not seen before in the Scala ecosystem, or to my knowledge, any ecosystem, just making it super easy to not only bake these laws into every type class, actually the companion objects of the type classes, but making it super easy to check them with just one line of code.
Great, sounds awesome. Can't wait to see it.
Any more questions?
Yes, this is Nicholas Rucat. So I'm fairly new to the Zeo community here, but this talk was, to me, very enlightening. It's a kind of like a revolutionary view on basically making FP programming, indeed, as John said, more elegant and fun. And when I see, and I work a lot with Lagom and Akka and those kinds of libraries and microservices, and I really enjoy it. But I can see that using Zeo Prelude could actually potentially have a big ripple effect in terms of like simplifying several libraries probably in the Zeo ecosystems. And so I'm wondering, what do you think is the roadmap about how long is it going to take to effectively propagate all of this preludedness, elegance, to the rest of the Zeo ecosystem, so that you could say to people, Zeo is a great way of programming in Scala. And people, instead of, I mean, I don't know about anything about Haskell, but, all the time people say, oh yeah, why don't you program in Java or in Extend, which is like some kind of like a FP wannabe type dialect of Java, or maybe in Python for Christ's sakes, right? And so I kind of like feel like I want to retain my competitive edge by actually using the best language to get my job done in the best way. And it feels like with this Prelude business and the way that Adam talked about the elegance in which we can incorporate that with law testing, it actually kicks ass. And so I'm wondering, like, when is it going to be like to the point where you have like this beautiful ecosystem that you can tell the world, you know, there it is, enjoy.
Yeah, I think that's a good question. I think that you're starting to see that now, but I think that what Zeo Prelude will give us is a common way to talk about structure across all these different libraries. Because right now they have no vocabulary to talk about that. But when that vocabulary is baked into every library, maybe as a separate project or maybe in core, depends on the library, then suddenly it makes it very easy to share that. And I think you get network benefits from that. And also you get the ability as an end user to learn one set of vocabulary and use that across all the libraries. And to know how, like if you make your data type and it has to satisfy laws, how do you do that? Well, you've learned it for one, you've learned it across all. So I think the types of network benefits that we'll see there and the way that things can fit together in a modular fashion will increase greatly with Zeo Prelude. I think it'll take a little bit of time to get there, but not too long. I think a year from now, all of that will have happened actually. And I'm really looking forward to seeing that happen.
Thank you.
Yeah,
Hi.
Great question.
I have a question, but I really enjoyed your talk, and I really appreciated the classification that this Prelude produces, and especially I think going back to the operation of flatten, which I think is the original definition of a monad in category theory, instead of conflating that with flat map, which makes people really confused.
Yes,
I think that is really brilliant.
Yes.
So now we don't have to use the word monad anymore. We can just say, oh, we have a flatten operation, which everybody understands. So I think that's great. And I think separating out the different algebraic properties, I think is brilliant. My question though is, the original motivation for monads was to introduce effects in a functional language, right? And I'm wondering, in your implementations, the various laws like commutativity and associativity, how do they apply? Do they apply to any effects at all? Because it seems like that's where the limitation is going to be. I mean, all the other algebraic data structures are wonderful, but when it comes to that, what are your experiences so far?
Yeah, you want to take that, Adam, or I can do it as well? You're muted, I think.
Sorry about that. Yeah, so it's a great question. I think it really starts with the problem being equality, because all of these laws rely on some notion of equality to test them. And the problem with real IO type effects is that there's really, if you're being principled, there's no way to do that. I can have two effects that do arbitrary things, and maybe I can check that they return the same value, but the reality is if I'm doing IO, I might return 2, but I might have launched 10 different network requests along the way, and you wouldn't be able to observe that from the return value. So I think there's probably a little bit more we could do. We've talked about having some concept of, I don't know if you call it test equality or quasi-equality, of at least equality to the extent we can measure it, of you give some inputs and we'll look and see whether we get the same outputs just for testing it. But I think it's important to just recognize that there is a fundamental limitation there and kind of not pretend you can define equality on things that don't have a well-defined notion of equality.
Mm-hmm. And another thing I would say is that if you take that flatten operation and you combine it with covariance, so you have the map operation, and then you have the flatten operation, then the composition of those two can satisfy additional laws. So that's something that you don't see now in the presentation, but like if you actually have flatten and covariant, you combine them together, that can satisfy new types of laws that are not present in covariant and not present in flatten. And I think maybe that's what you were hinting at. But that flatten operation, if you have map as well, you can implement flat map. So it's as powerful, it's just expressed in a totally orthogonal way where there's no overlap. You know, flatten is as primitive as it possibly can be. Map is as primitive as it can possibly be. They don't overlap at all. They're orthogonal. You combine them together, and now you can generate flat map. Flat map is another example of the reason why it's structured that way is because it's useful to structure it that way. When you're using it, it has nothing to do with, like you said, it has nothing to do with the category theory representation of a monad, which is a monoid in the category of endofunctors. It's like we have two of these things and we smash them together into one, and that's the flatten operation. That's join.
All right.
All right. Anything else?
John and Adam, that was absolutely fantastic. Fantastic. The talk, the prelude. Now I know what you guys have been up to. I can't thank you
for the huge pains and technical difficulties and everything. I can't believe just how much trouble we ran into tonight, but I appreciate everyone.
It was me who was supposed to apologize.
Not your fault. It's not your fault.
Yeah, I really can't thank you enough for doing this talk at Scala, and hope it didn't put you off coming back at Scala, and hopefully one day in person again. Yeah.
Yes, in person where we can't be bombarded by trolls.
That's right. That's right. That's right. First time for everything. It was the first time it happened to a meetup that I was running. So now I'll be on extra guard next time.
Yeah.
I've thought of a few ideas for next time. Let's see what's best. Hopefully there'll be no next time.
Get a few volunteers to dry run it first and cause as much mayhem as they can, and see if you can shut them down.
Yeah, absolutely. Absolutely. But yeah, no.
Question if we've got time.
Go for it.
At the beginning of the talk, John, I think you were talking about how you could have, like, say, a monad instance for like a type, and then it could actually like widen to the monad instance of another type. And I think you, in kind of reference to the idea that like we get a lot in like cats where you do like dot sum on something and that turns it into option automatically and whatnot. I was actually expecting to see variance on the F parameters, like on the outside of the F as opposed to the inside, to solve that problem, but I didn't see that. So does the library handle that very well, or is it still kind of a hole?
I think that makes sense. The reason why you don't see it in the library is because the Fs generally occur as inputs and outputs. But in your own type classes, for example, if you're doing tagless final, you're going to have a bunch of F constructors. It's going to appear as an output parameter. So I actually recommend you use the plus sign for that. But yeah, I think all the operators that I can think of in Zeo Prelude, the F occurs as both an input and an output. So you can't make that covariant, unfortunately. But if you can, then definitely do it, because it works in a lot of cases. And when it does work, it's really, really nice.
Okay.
Yeah.
One other question, would you be
you're cutting in and out. I don't know.
Yeah, it was a bit choppy.
Yeah, I think we lost Britta there. John, at least we're not standing in the middle of the street for you taking questions like last year, right?
Right.
So in the meantime, if I may, I have a follow-up to Nigel's question then. Since you said, John, that in our applications, you could have like basically two F parameters, one for just inputs and one for just outputs. Had you guys configured in Zeo Prelude the idea of perhaps saying, well, somebody might actually, for legitimate reasons, want to put some covariance on the F for the input purposes or output purposes. So instead of using the same F for both, why don't we have two parameters, one always for inputs and one always for output?
So we use that technique on lower kind of types all the time in the Zeo ecosystem. So in order to make things infer very well, we'll split invariance into the covariant part and the contravariant part, have two separate type parameters. It works beautifully. Now, the reason why I wouldn't necessarily recommend doing that on the type classes themselves is because it's a niche use case and it's going to complicate the design of the library. And this is something that I talk about when I'm trying to teach library design, is that you have to make trade-offs. If you want to make it really good at some things, it has to be not so great at others. And absolutely, if you wanted maximum covariance, contravariance, so subtyping relationships, then you would split things up like you would split associative both up into the covariant part, which would be an F, and the contravariant part, which would be a G, or vice versa. And you would annotate one with minus and one with plus. These would be the higher kind of types. F and G would have kind star to star, and you would annotate them with plus and minus. And then your operations would support an input type that is potentially different than the output type. That would give you a lot of power and a lot of flexibility that would be used in a very small number of cases. So in my view, if you're aiming for a mainstream library, then that would probably not be the best trade-off to make, because it will complicate the design and only address niche use cases. But nonetheless, you're right that would actually give you much better type inference for those use cases. And also, you would be able to describe things using that structure that you can't describe using the current one, in which you have a single F, a single data type that it's invariant in. Okay, anything else?
John and Adam, thank you so much. I think everyone's ready for a glass of wine now and to digest Prelude and the unnecessary drama at the beginning of the evening, right?
Time for a glass of wine, for sure.
Yeah. Thank you so much for starting from scratch and doing your talk again as well. I really appreciate it.
It's no problem.
Stamina.
Yeah, that was amazing. Yeah, the second effort was even better. So
I'm glad to hear that.
I had to rush my introduction of John, though. I feel like I didn't introduce him as well as I could. I tried to condense it, as I thought everyone's waiting. They don't want to hear me. So sorry I didn't introduce you better the second time around.
No worries.
Let's do it one more time.
No. I'm out of here. It's been fun all.
Thanks, guys.
All right.
Thanks, all. Have a great evening.
Thank you.
Thanks, John, again.
Thank you, John.
Take care, everyone. Bye, everyone. Bye.